Let us continue our discussion of discrete mathematics subject, and let us look at the syllabus points. If you look at the syllabus points, we are somewhere here: logic, propositional logic, predicates and quantifiers. So in today's discussion, we'll be speaking about well-formed formulas, inference rules, and a few proofs for tautology and implications. So what are well-formed formulas? This we have derived from this link googled, that is cs.odu. So all the contents of well-formed formula are derived from this. So basically well-formed formula is what? It's an expression. It has what? Variables, parentheses and connective symbols. Which are the connective symbols? The connective symbols are and or kind of. So there are few rules for constructing the well-formed formulas. Let us say we have a predicate like this, p of x comma y, where p is the predicate, x comma y are the variables. This kind of formula is called as an atomic formula. Now, what are the rules for well-formed formulas? True and false are well-formed formulas. Specific propositions and propositional variables are well-formed formulas. Atomic formula are well-formed formulas. Let us say A, B, C are well-formed formulas, then not A and B, A or B, A implies B, A double implies B are also well-formed formulas. If X is a variable and A is a well-formed formula, then for all X A and there exists A are also well-formed formula. Now, how do I check whether an expression is a well-formed formula or not? So what we can do is we try to convert that well-formed formula into English sentence. And if the representation and translation is proper and correct, then it is a well-formed formula. Regarding implication, I have taken from this link, googled from this link, libertex.org by Kwong actually. So what exactly is an implication? We know it. Okay, implication is denoted by like this. P implies Q. What is the meaning of that? If P, then Q. There are multiple meanings of that. P implies Q can also be said as P only if Q. Q if P. Q provided that P. So all of them may mean what? P implies Q only. Now, in this P implies Q, this P is called as the hypothesis, or it is called as the premise, or it is called as the antecedent, while Q is called as the conclusion or consequence. Conclusion or consequence. Now, what is the importance of implication? So, in logical argument, implication plays an important role. Suppose an implication is true. So, whenever a hypothesis is satisfied, the consequence will also be true. That's why the implications are also called as conditional statements. Conditional statements. Let us look at few inference rules, and this inference rules material I gathered from this tutorialpoint.com, discrete mathematics rules of inference. So what exactly is inference theory? Okay, it is analysis of validity of formula from the given set of premises. You know what is the premise? Premise is a hypothesis. Okay. Now, let us look at each of the inference rule. The first one is addition. Okay. If you look at it, it is very, very simple. Say for how do I read this inference rule? If P, then P or Q. As simple as that. Let us connect with that an example. Let us say P is he studies very hard. Okay. And there is something called as either he studies very hard or he is a very bad student. So here Q stands for what? he is a very bad student. As simple as that. Now, how do I represent this inference rule? P is there, Q is there, then P and Q is there. Okay, so here P and Q are what? Two premises. So here we are using conjunction and. Okay, so let us say P is he studies very hard. Q is he is the best boy in the class. So we have to perform P and Q. Then it will be he studies very hard and he is the best boy in the class. Let us go for the next. If P and Q is there, then P is there. So let us say P and Q is represented as he studies very hard and he is the best boy in the class. Then what will be P? He studies very hard. As simple as that. Next inference rules is modus ponens. If these are the two things, P implies Q is one premise, P is one premise, then Q is there. So let us say P implies Q is represented as if you have a password, then you can log on to Facebook. So P is what? If you have a password. Okay. So what will be Q then? You can log on to Facebook. The next tool is modus tollens. It is represented as P implies Q, not Q. If they are there, then it will be not P. Same thing. I'll represent this P implies Q as if you have a password, then you can log on to Facebook. So here Q, not Q is indicated as you cannot log on to Facebook. So naturally not P will be represented as if you don't have a password. You do not have a password. Next inference rule is disjunctive syllogism. So if you have like this, not P, P and Q, then Q will be there. So for example, not P is represented as ice cream is not vanilla flavored. P and Q is represented as ice cream is either vanilla flavored or chocolate flavored. So naturally Q will be what? The ice cream is chocolate flavored. The next inference rule is hypothetical syllogism. If we have P implies Q, Q implies R, then P implies R will be there. Similarly, constructive dilemma is represented as P implies Q and R implies S, P implies P or R, then Q or R. Destructive dilemma is represented as if we have like this, P implies Q and R implies S, not implies Q or not S, then not P or not R will be there. Let us look at few proofs. So we have to prove that P and Q implies P. So this double arrow will be replaced by single arrow. So it becomes P and Q implies P. So it is A implies B. So that will be represented as not A or B. So that will be not P and Q or P. So I'll be applying this not to individual terms. So not P or not Q or P. So not P or P will be truth. Okay. So that is a tautology. So Q, that is a not Q. So T or not Q. So again, it's a tautology. We have a relationship like this. So let us take one at a time. I'll be taking the first one. P implies Q implies R. So this Q implies R can be replaced as not Q or R. Okay. So P implies not Q or R. It is already there. P implies. So first one is proved. So now same thing I am taking P implies not Q or R. So that is A implies B. So that can be represented as not A or B. So not P or not Q or R. So not P or not Q or R. So that can be represented as not P and Q or R. So that will be represented as P and Q implies R. So second one also is proved. P, okay. We have to show these two are equal. So on the left side, I'll be taking this P implies Q implies P. So this Q implies P can be represented as not Q or P. So again, this A implies B form is there. So I can represent it as not P or this relationship. So I'll be taking out P here. So not P or not Q. So T or not Q will be tautology. So similarly, left side is T now. On the right side, we have not P, P implies Q. So this P implies can be represented as not P or Q. So this again can be represented as A implies B form converted to not A or B. So not of P or not P or Q. So this becomes P or not P or Q. So this P or not P will be true or Q. So that becomes a tautology. So both are T. So left and right side are proved. Next we have to prove this. So I'll be taking P implies Q and R implies Q. So this will be not P or Q. This will be not R or Q. So this representation I am converting C here now. Not P and not R or Q we are taking out. So that becomes not P, not is taken out as common, so not P or R or Q. So that can be represented as P or R implies Q. That's what is the conversion. Okay, so with this we have stopped our discussion.